Welcome to Chapter 7, the fourth part screencast for covalent bonds and molecular structure. In this screencast, we're going to look at electronegativity and bond polarity. Although we've been dealing with chemical bonds as being ionic or covalent, in reality, chemical bonds are usually not either purely ionic, where the electrons have been completely transferred from one atom to another, nor are they purely covalent, where the electrons are perfectly shared exactly equally between two atoms. Most chemical bonds are somewhere in between the extremes of pure ionic and pure covalent, and the electrons are shared unequally between the two atoms involved in the bonding. This kind of bond happens when the two atoms that are bonded together differ, at least somewhat, in how strongly they attract electrons. Chemists use an idea called electronegativity, which is abbreviated EN and sometimes symbolized by the Greek letter. It looks like an X, but it's chi. And this is an overall measure of how much an element wants to attract electrons. So it's a measure of the ability of an element to attract electrons. This idea is due to the famous American chemist Linus Pauling, who won a Nobel Prize for chemistry and also won a Nobel Peace Prize during his career. Electronegativity values, due to Pauling, are typically in the form shown on this chart, where fluorine is the most electronegative element. It likes the electrons the most, and it has the highest electronegativity value of 4.0. Electronegativity values decrease as we go down a column or across a row to the left, and the lowest electronegativity values are found in the bottom left of the periodic table. Elements that attract electrons strongly have high electronegativity values, and examples of those are things like fluorine and oxygen and nitrogen and chlorine, elements up in the top right corner of the periodic table. They like electrons, they attract them strongly. Elements that don't attract electrons strongly and have low electronegativity values are typically found in the bottom left corner of the periodic table. Things like cesium or rubidium or barium, alkali metals, alkaline earth metals, and they don't like to grab electrons that much, so they have low electronegativity values. When we have two atoms bond together, and those two atoms have different electronegativities, then they don't share electrons equally. An example of this would be the molecule HCl, and hydrogen has an electronegativity of 2.1, chlorine has an electronegativity of 3.0, which is higher, and so chlorine gains electrons relatively speaking, or attracts electrons compared to hydrogen. And the electrons that are nominally shared in this chemical bond are pulled a little bit more towards the chlorine, a little bit less towards the hydrogen. The atom that has the higher electronegativity value is the atom that grabs electron density, and because electrons are negatively charged, then that atom gets a slight negative charge. And in the case of HCl, that atom is going to be Cl because it has the higher electronegativity. The atom with the lower electronegativity gets less electron density near it, and less negative charge means that relatively speaking it's slightly positive, and in the case of HCl, the atom that gets the slight positive charge is the hydrogen, the less electronegative of those two elements. When we get a separation of charge between two atoms in an unequally shared pair of electrons in a bond, this is called a dipole. Di for two, and pole for the two poles or opposite sides, positive and negative. And the bond is then called a polar covalent bond. So polar means it has a dipole, and covalent means the electrons are shared, but they're going to be shared unequally. And how we represent a polar covalent bond is one of several different ways. One is we draw an arrow pointing from the atom that has the slight positive charge towards the atom that has the slight negative charge. So it's kind of the direction the electrons are being pulled in. We can also do a delta plus and delta minus above the atoms as appropriate. The atom that has the slight positive charge gets a delta plus. This is the lowercase Greek letter delta, and it means partial charge, not a full charge. And then delta minus is the atom that gets the more of the electron density and gets a partial negative charge. And then we can also do an electron density map or diagram, and often these are color-coded. In this case, the blue indicates a slight positive charge, and the red indicates the side of the molecule with a slight negative charge. Now, how big the dipole is, the magnitude of the dipole, which corresponds to the degree of polarity of the bond, depends upon the difference in electronegativity between the atoms that are bonded together. Now, this is a continuum, but as a very rough guide, what we say is that when the electronegativity difference between two atoms is quite big, like 2.0 or larger, then we essentially have ionic bonding. The electronegativity difference is such that is large enough that the electrons are transferred from one atom to another, and we basically have ions being formed. Now, on the other hand, if we have atoms that don't differ very much in electronegativity, when their electronegativity values are 0.5 or less than 0.5, then that's pretty equal sharing, and we're going to just call that a covalent bond. And if we're between those two, then we have sharing that's unequal, and that corresponds to a bond to being polar covalent. Now again, this is a continuum. There's no real harsh or discrete specific cutoff between ionic polar covalent and nonpolar covalent. Different texts and different people use slightly different places to make the transition. We're going to go with what our text does for 2.0 or above for electronegativity difference being ionic, less than 0.5 being nonpolar, and then in between that being polar covalent. But it's really a continuum, and at this end are more ionic bonds, at this end are more covalent bonds. These would be larger polar covalent, these would be smaller polar covalent, and the general trend is the bigger the electronegativity difference, the more polar the bond, the smaller the electronegativity difference, the less polar the bond. All right, let's classify some bonds as ionic, polar covalent, or covalent. And we'll start with cesium chloride. Cesium has an electronegativity of 0.7, chlorine of 3. So the difference between those two is 3.0 minus 0.7, which is 2.3. And that is a pretty big electronegativity difference, which corresponds to an ionic bond. Electronegativity difference bigger than 2.0. Carbon-hydrogen, as another example. Carbon has an electronegativity of 2.5. Hydrogen is 2.1. The difference between those two is 0.4. And 0.4 is a small difference, less than 0.5. We typically just consider covalent. Too little polarity to count as polar. And so this is going to be a covalent bond. And the PO bond, phosphorus to oxygen. Phosphorus has an electronegativity of 2.1, oxygen 3.5. The difference between 3.5 and 2.1 is 1.4. That falls in the polar covalent region, where the electronegativity difference is more than 0.5, but less than 2. And this would be a fairly polar covalent bond for phosphorus oxygen.